Bom dia a todos. Vamos dar continuidade aí a esse evento, o terceiro simpósio de datação por métodos físicos, aplicações de arqueologia e geociências, né? E agora nós temos uma sessão com 3 professores que será um prazer para mim ser chair dessa sessão, né? Então, vamos falar aqui. Eu sou Suzana de Souza Lage, professora da Universidade Federal de Sergipe, e agora nós vamos mudar para inglês, porque a sessão vai ser toda em inglês, as apresentações serão todas em inglês, então vou mudar um pouquinho a língua aqui. So the next presenter is Professor Debashish Sengupta. He is presently working as professor, high administrative grade at the Department of Geology and Geophysics in the Institute of Technology, Kharagpur, West Bengal, in India. He was head of the Department of Geology and Geophysics from 2013 to 2015. He has actively been involved in TL data, in TL dosimetry, estimation of environmental radioactivity and technological enhanced radioactive, and its role in environmental geosciences, radon and manometry. Till to date, 14 students have successfully completed the doctoral studies under his supervision, and some more are in progress. He has published more than 100 research publications in reputed international journals and presented numerous invited talks both in India and abroad. He has been a visiting professor, senior visiting professor in reputed universities, institutes in Brazil, Spain, to name a few. Regulatory framework in various countries have adopted quite a bit based on seminal work undertaken by him, his group, and his research group. He has won numerous awards along with the recent award for sustainable development and ambient environment by conferring by the gold medal and plaque of honor instituted by Society of Geologists and Applied Technologies, Odisha, India, namely SMT Vina Rumwal Memorial Award 2020, awarded once in 2 years only. So, Professor Sengupta, it's a pleasure to have you here. The floor is yours.
Okay. So, I'm thankful to, I should say, muito obrigado to Professor Suzana. And of course, I have my heartfelt thanks to Sonia for giving me the opportunity. And of course, since I was there, I have wonderful memories of with Professor Shigeo Watanabe and Professor Sonia Tatumi and other people there, almost 23 years back. And so it was a wonderful stay there. Of course, though I was new in terms of Portuguese and various aspects. So I will start the talk, and if I would be happy to answer. And it's more of a talk where I have made it very, very interdisciplinary. Okay, so and this is because why I have made it disciplinary, because this is going to be one of the major aspects in the coming at least few decades, because I believe and I have found out that technologically enhanced natural radiation is increasing like other contaminants, not only in the atmosphere, not only in soils, not only in rocks, but also in uh, the groundwater and uh, ocean water, etc. Okay, so can I go to the PPT? Then I will. Alvaro, can I go to the PPT?
I'm not in. I can't see your PPT. Please put in full screen mode.
Okay, now it's okay?
Okay,
Yes?
just yes, put in full screen mode. Yes,
One. Okay.
yes, it's
So
work.
basically, what I'm trying to show uh, is the thermoluminescence dosimetry, uh, and of course, using nanophosphors in heavy minerals along eastern coast of India. This is just a study area, but it must be applicable to the entire planet Earth, and of course, other planetary systems. So it is not that it is true for India only, but more true for India because of various reasons. Now, this is the part along the eastern coast of India where we have done almost more than 50,000 measurements along a total spatial extent or lateral extent of about few hundred kilometers. And very soon we would like to cover the entire up to Kerala, say about 500 kilometers spatial extent. Okay, and here is some handheld portable counter, but we have various other systems to supplement the data. And earlier, most of these handheld counters, they're not used to that extent because we had various types of other supplementary data where the radioactivity was not considered to be so essential, especially in earth sciences. And why I'm telling in earth sciences, because this is very important, not only for an earth scientist, but anybody working in applications related to applied physics, related to uh, human civilizations, etc., including archaeology, including how much Indo, radon, and thoron is important in dwellings, which type of material to be used, and what is the effect of industry in contaminating, not only in terms of so-called important uh, atmospheric gases, global warming gases, but also in terms of radioactivity. And nowadays, you find that we have elevated levels of radioactivity, and that requires a very reliable measurements on dosimetry. Okay, so this is prime importance. Now, why we have chosen the area? Because if you see this is the coast, and here we have the eastern part of the eastern coast, which is known as the Bay of Bengal, and towards uh, my right in this part we have it is going towards Sri Lanka and then going towards the Indian Ocean. Now, all these black patches are rich in heavy minerals, and one of the major heavy minerals uh, which we are working on is monazite. Please remember that monazite is having rare earths. When I say rare earths, right from lanthanum to lutetium, quite a lot of them in very high abundance, and some of them may not be so high. But in general, all the monazites are very high in rare earths. It could be the light rare earths or the heavy rare earths. Now, these are very, very, strategic minerals. Please remember, all the rare earth oxides are of strategic significance. Then the combination, since it is monazite, it is thorium, it will be thorium. And of course, you have the phosphates. So, all the three, that is rare earth, the thorium, and phosphate, they are going to be extremely useful in terms of as economic resource in the future. Only thing is, you have to uh, extract the rare earths in such a way that it is the thorium doesn't affect it to that extent. And then after extracting thorium, you allow the phosphates for various applications, including agricultural purposes. So it is a triple resource thing where rare earths can be extracted, by various processes. We are trying some processes, especially which are environmentally sustainable or sustainable. You can extract it in a very sustainable manner. And there are various types of methods with chemical engineering and other research groups. We are trying that out. The second thing is that, as I said, the thorium is quite important because, especially for countries like India, which have large rare earth deposits, India is having the second largest thorium reserves in the world. So, uh, this thorium we are trying to utilize for in nuclear power reactors after being converted or transmuted to uranium 233. So it is not directly fissionable by neutrons. You can convert it to uranium 233, and then of
I'm
course
sorry, Professor Dolly. I think I noticed see your passing your pages from PPT. You can click in F5 button, please.
I can click at
F5.
F5. Okay. I have done it. I don't know. Something is happening.
No, here in the bottom part of the PPT, that clicking the last option is in the
Left
uh,
or right?
yes,
Right. I'm not seeing
next
anything.
to the option that is selected now. There is like a book in the right line, in the right side, in the
On
bottom
the
part
right
of the
side, yes.
yeah, the last one, last
Last
icon,
one.
the last
Last.
one.
Okay.
Yes, that is.
Now.
Yes, oh, now it's working.
Okay. So I'm sorry for some small amount of
No, no,
disruption.
no problem.
Now, so I was talking about that the deposits which we are talking about uh, are extremely useful, and our fourth stage of nuclear power generation is going to nuclear based on nuclear power reactors is going to be based on thorium, right? So this is one of the major uh, applications. The other is, of course, India being a primarily agricultural intensive country, uh, they require phosphates, and these phosphates can be used provided it is free of thorium, means as low as possible. Okay, so this is the overall thing. The abstract I have already put it, and anybody can see it. So now, coming back to a very important thing, why this is not only of local significance, why it is of global significance. See, anybody in any country in the world, please remember that these sort of work is very, very important. Now, here, these are the coastal places where we are presently, we have worked on these aspects. We already have started. This is the state of Orissa. This is the state of Andhra Pradesh. Here is another country close by, uh, very close by, which is Bangladesh. This part is a small island country known as Sri Lanka. Here also we are working on, and all these have large coastal rare earth deposits. That means heavy minerals. Now, China, alluvial and coastal places, let me make it very clear, just like the world depends on countries from the like Saudi Arabia, Qatar, and Iraq, and other things for conventional hydrocarbons. China is the biggest exporter of rare earth oxides. 95% of the rare earths required in mobiles, in your computers, in various applications, in defense, in uh, photographic cameras, in catalysis as a catalyst. All these things come from China. So China has got the major, you can say, a strategic control over all the rare earth deposits and all the rare earth oxides which are supplied to various countries. So China has been successful, just like you have the hydrocarbons being exported from the Persian Gulf and various countries, and of course there are other countries also like Russia, which supplies them. I'm talking about conventional hydrocarbons, not the shale gas and etc. Okay. Now, other important thing is these sort of things are present here also. You have in Brazil these coastal deposits and the rare earth deposits here also, and of course Thailand and Malaysia. Now, this means that when the Earth formed close to 4.5 billion years, subsequently it differentiated, and then the plates started migrating. We call the Gondwanas, and then the plates started migrating. Now, initially, Sri Lanka was almost attached to the Indian plate, then it moved little bit toward the Eurasian plate, and that is why these areas are rich. Brazil also has got a lot of this thing because some sort of a initial, if you reconstruct the plates, you will get that this is almost close to the initial Gondwanas, and that is why this is there. Antarctica, for example, this part is almost similar to the rock types and the rare earths present in Antarctica. So, and some parts of Africa also, coastal parts, which are not studied to that extent. Here only we are talking about which we have been studying, and Australia is also being heavily studied. Extensively, publications are there in the open domain. So this is very important that this is not only important for this part, this is not only important for Sri Lanka, Bangladesh, of course China. We are not able to extract it, rare earth oxide, in a suitable form because of various reasons. In Brazil, we have this, and of course, some parts of America. Now, most of these countries, China and other countries, they extract rare earths from a mineral known as bastnasite. This bastnasite is a fluorite, and it contains radioactivity, but lesser than monazite. But it contains quite a lot of bastnasite is radioactive in nature, so you have to remove the radioactive part, uranium thorium, and then make the rare earth oxide, extract it, and then take it and then convert into the metals in the metallic form. Then, of course, it is exported. So, in India, we have been working right from the beginning, and we have been fortunate enough. We did subsequent to coming to this institute, my research group worked on almost all these areas, and now we are going little bit down. Okay, and we are also working on this area, but in the western part, we have worked on TL dating. Initially, when we started, we had dated some of the ancient flints and the sand dunes and all those things in this part of western part of Sri Lanka. Okay, so this is the data which we had, which was published in Earth and Planetary Science Letters. Okay, with Professor Singhvi, and we did some work on this part, and you see that the close to this part, most of the regions we have got not only the radiocarbon dates, but we had very good TL dates, which were the probably one of the first few dates of thermoluminescence on these things. Now, one thing, let me make it very clear that when you get any date like thermoluminescence or optically stimulated luminescence, especially when I talk about this, we are talking about right from very young ages, few hundred years, to roughly about 50,000, 60,000 years or so on. Okay, in the denominator, there is a term known as dose rate. So you should have a very reliable estimation of uranium, thorium, potassium. That is very important. The other pertinent aspect is, was the uranium in the particular mineral very close to quartz or feldspars in this ambient environment? Was it in equilibrium, secular equilibrium or not? Now that has to be understood very well, whether you do for archaeology, whether you do for sediment transport, whether you do for any radiation dosimetry. So please remember, that the amount of uranium and thorium and potassium in the minerals, it has to be connected to the thermoluminescence ages, because without that, it is not going to make any sense. So the entire luminescence dosimetry and dating applications is heavily dependent on earth sciences and other material sciences also. Please remember that is very true. Why? Because uranium, as you know, it occurs in +4 and +6. +6 is easily leachable. It is very labile and mobile. But thorium occurs in +4. Generally, it is resistant in the pH range of 7 to 9. But if the pH is very, very low, uranium +4 and thorium +4 can also get leached out in typical environments. Okay. So please remember, between 7 to 9 pH, they remain, except for uranium +6, they remain almost in a closed system. Otherwise, they can migrate. Then, apart from that, of course, there's a lot of voids and all those things. The radon can migrate, and then whatever you are estimating in the laboratory, that may not be true for 100 years or 1000 years, or whatever the TL age or OSL age you have obtained. So please remember, the denominator, the dose rate has to be very, very reliable. It should reflect the in situ dose rate, not the laboratory estimated dose rates. You can use high-end equipments, high purity germanium detectors, or BGO detectors, or cadmium telluride detectors. But the problem is it valid for 100 years, 1000 years, or so on? So this is very, very important. And here comes the role of geologists, I would say earth scientists, because geology and geophysics is all similar, means intercombined, intercorrelated. And then, of course, if it is a work of archaeology, you have to talk to the archaeological people who will understand what is happening, whether there is calcrete, what happens to the calcrete formation, or there's flints, or there are other obsidian glasses, and whether they are related to the particular strata. Okay, but the simple radiocarbon or AMS radiocarbon may be selectively used, but TL has got a much wider range. Okay, so this is important. Now here I'm talking about certain environmental TL dosimeters. These are the card-based thermoluminescent dosimeters, which has been used in the dwellings, in the houses close to a uranium mine, which was one of the richest uranium mine. Now that it is no more, because there are other uranium mines. Almost all the uranium from here has been utilized. This is a part of what is known as the Shingun Shear Zone. It is in the state Jharkhand, and this region is known as Jadugoda. So we did some in 2005-6 onwards. We did a lot of measurements, and we had put these twin cup dosimeters in various mud houses. And fortunately, I am telling you, we found that the dose rates were not so high, and you see that we have calculated the outdoor gamma dose and the annual outdoor dose rates, and you find that lot of villages we have studied. These are the villages which we have studied, and we have studied for different seasons. Why seasons? Because we find that the dose rate has got some relationship with the change of seasons. Now, earlier, the seasons was spanning 3 months every year. Now, of course, because of extreme conditions in the weather and because of global climatic change, the spring and summer and monsoon are not really spanning 3 months. Sometimes they span and sometimes they're not. But up to 2010, the spring, summer, monsoon, winter was almost spanning 3 months. Okay, so this was done, and then of course we made these measurements with these sort of thing. And please remember, we used dosimeters, calcium sulfate with dysprosium. Again, dysprosium is a rare earth. So please remember, most of the dosimetric material require rare earths. Okay, So I think one of the major things which we should understand that rare earths are also very important. Nowadays, in medical dosimetry, rare earth is extremely important. I'm not talking about medical to that extent. Of course, we are working on some aspects which are different little bit. Maybe I can share some of my publications. Okay, but the rare earths in their typical crystal lattice is what is giving rise to the traps in the forbidden gap. And that is very important. And that makes it sensitive and luminescent. Okay. Now, this is the TLDs which Professor Dhole from University of, who is going to give the talk next to me, he has been kind enough. We are jointly working on this. There is another TLD, the nanophosphor. This is a European and another phosphor he is developed. We are trying to use this along the coast of Orissa due to various reasons. I'll come down to the reasons, a couple of reasons, not all, why we are sticking to the eastern coast of India. Now, you see that the TLD by calcium sulfate dysprosium, which was quite well known, and even it is used very effectively. And these are some of the useful dose ranges, fading, and etc. So, we are trying to utilize this also, and apart from other nanophosphors, to try to make it more reliable. Now, radiation dosimetry by TL phosphors by itself is not going to answers quite a lot of queries in terms of applications. We have to integrate it field-based radiometric surveys as well as uh, uh, the other radiometric surveys, that is the laboratory assaying, radiometric assaying in the laboratory. Now, you can assay it using simple sodium iodide activated with thallium or cesium iodide and so on. But we are using high purity germanium in collaboration with institute, which is Variable Energy Cyclotron Center, very close by, about 100 kilometers from our institute. Okay. Now, coming to this, this is what is the various mines which were used for the last couple of years, except for Jadugoda, which is not, which is almost finished for the last 50 years. It has given a good amount of uranium. The rest are all being used. Now we have gone to the southern part of India, where instead of a particular rock type, it is present in a limestone-rich environment. Of course, limestone, sedimentary limestone will not contain radioactivity or uranium, but it is present in particular organic materials or fossilized materials, which is known as stromatolites. So all dolomites, sandstones, and limestones, if they contain a lot of organic material, you will have a lot of uranium. And these are mostly inland deposits, means it is in the continental lithosphere or continental part. Okay, so these are some of the things still working uh, actually, and most of these mines. And we did some surveys, as I said, using a particular technique known as resistivity. This is electrical resistivity sounding, and we have done this, and then we have measured some current density, and then we got some resistivity values. And of course, the resistivity values, I'm sorry, I have not put it here. The resistivity values indicate that at the lower depth, the basement is having completely a granite, which is reasonably radioactive, not very radioactive now, and the basement is completely free of voids or any fractures or microfractures. So that means the vertical percolation because of any uranium-rich solution is not possible. Even the spatial migration is not possible if you have some, tailings pond where you have to store the waste. Okay, so most of these mines are having a tailings pond where low radioactivity material is stored. Nobody can use it. It is, cannot be used for plants. Means plants hyper it, but it cannot be used as feeding material for animals. Neither water is used for potable water. Okay. The other thing very unique is both radioactivity and resistivity can be combined. Resistivity sounding can be combined, and you get typical values for resistivity for contaminated water. Same with you can make with radiometric data, and you can also get in nature of the rock type both using radioactivity as well as the uh, resistivity. So what we are doing is all the dosimetry which we are doing here in most of the cases close to uranium mines. Earlier we did it, and now we have proceeded and we are doing much better. This was mostly in terms of calcium sulfate, as I said, with the dysprosium, and we found the granite to be at the basement was very high resistivity, few thousand ohm meter, and it is completely impervious or non-permeable. Okay. Now there's another thing which we have been using quite a lot is we have a lot of hydrocarbon stations and petrol pumps and other things, and we have the rivers close by, and we have done some non-aqueous phase liquid, and then we have done some radon and other measurements, and then we find that the contamination, you see the contaminated zones using both radioactivity and resistivity. So this integration of geophysical methods with radon and then subsequent modeling tells that this, the hydrocarbon blobs, which we call non-aqueous phase liquid, this is going to be very, it will get concentrated. This will become, the older it gets, it becomes more problematic because what is happening is that it affects the plants. All the agricultural uh, things growing there in the region, including trees or anything, is going to get contaminated. And that is why one should worry that what sort of a groundwater we are utilizing, not only for potable water, but for utilizing in agricultural purposes. And this is becoming very acute because apart from arsenic, which is becoming very common in parts of Bengal and Bangladesh, parts of China and Vietnam for rice cultivation, even these things are becoming very, very important. And hydrocarbons also have radioactivity, especially conventional hydrocarbons, and some large amount in case of shale gas. Shale gas gives rise to lot of radium and lot of radon, and so the past water for hydrofracking creates a lot of problem. And one has to be, very sure where you store the hydrofracked water subsequently. Now, this is where we are now putting all our dosimeters. We have made numerous measurements along this with handheld counters. We have taken few hundred, more than 500 samples from each of these parts. And this is a river, and this erodes all the rock here. And this is a perennial river, comes from very high altitude. How much? 1,000 meters. This is basically uh, uh, precipitation fed river, rain fed river, and this converts all the material to what is the beach sands, and all these heavy mineral beach sands you find very high radioactivity, especially thorium. Okay, and the region where we get mostly are what is known as the berm region, BERM. So the fossilized dunes have got radioactivity, but the berm is having maximum amount of radioactivity. The four dunes and other parts do not have so much of radioactivity, and the continental shelf also doesn't have radioactivity. Okay. Now, the other important thing, which is very, very important, is that most of these heavy mineral deposits along this coast, this goes down to Andhra Pradesh and down towards southwest to Tamil Nadu, and we are studying that part also, including, as I said, Sri Lanka and Bangladesh. Uh, Towards the northwest, we have, no, sorry, northeast, we have Bangladesh, and there also a lot of heavy minerals are found. We are studying that also. Now, The problem is that all these things have originated in the last 10,000, 15,000 years. We have some ages on this. We are trying to get more ages based on various OSL dates. And then, so this is because of the marine transgressions and regressions primarily. And then, of course, this is the erosion of the rock here, which is present. These are typically known as charnokites and the granite migmatite gneisses. Okay, so that is why the same things happen true for Sri Lanka, where we are working on one of the richest uh, rare earth deposits in the world. Okay, now so this is very very important. Lot of rare earths. Which are the rare earths enriched? We have found, we have done a detailed study. Neodymium is of the order of 2000 ppm. Similarly, with dysprosium and cerium. So, lanthanum is there very high, but cerium, lanthanum, dysprosium, neodymium are some of the things, and even samarium. Now, all of them have applications, and very soon the new computation techniques, that is the hardware, is going to have rare earths. All the hybrid vehicles are having rare earths. In which form? The rare earth magnets, which contains neodymium. Your clean energy, the solar cells as well as windmills, they contain rare earth magnets. Normal magnets are completely useless. So it is the rare earth magnets which are making a lot of changes, and all these rare earth magnets either have neodymium or some other rare earth. Now, for various type of LEDs and etc., you have dysprosium and other minerals. Of course, europium is also used. So please remember, these are very, very rich in rare earths. The thing which I wanted to make it very clear is all this area is now, for the last 10 years, is getting affected by cyclones and super cyclones. Very recently, we had a cyclone here, and the frequency is increasing because of global warming. So, if I can get some amount, which we are trying to do, based on uh, the dosimetric data, based on uh, the heavy minerals, especially monazites. We are studying monazites in detail, even single grains of monazites of the order of 50 to 100 microns. We can pick it up and we can study. So we are trying to understand that uh, what is the effect of the cyclones and the super cyclones, even to some extent tsunamis, and the effect on the erosion, because India is a peninsular country, peninsular subcontinent, and we have 6100 kilometers of coastline. Now, if heavy erosion is there and sea level rises and we have coastal inundation and population, already I need not tell you, is almost more than 1.2 billion people. So we have to bother about these coastlines very well. And this is true for all the countries, whether they have a lower population or higher population. Okay. So the effect of global warming on the frequency of cyclones and other things, subsequent to the marine transgressions and regression, is very, very important. And when we have well-defined monsoons means the rainy season, 3 months, that is also getting altered, and this aberration is always there. So this sort of things we are trying to study using the heavy minerals, because most of the heavy minerals like monazites, they represent very well, they don't get altered to that extent, and they can give a very good idea. And of course, why radiation dosimetry? We can do DL dating or OSL dating, and we can also find out, because we have lot of, I will show you some of the boreholes where we have measured, and you see that the dose rate based on microsieverts per hour. This is handheld counters, and we have stacked it up, and you see how these things changes. And this is thorium to uranium ratio is becoming very, very high. One thing, let me make it very clear. For a typical crustal rock on this planet Earth, our planet, our home planet Earth, the thorium to uranium ratio for a normal rock will be about 3.8. There are reasons for that. We can discuss on these aspects. But in this region, you'll be surprised that this thorium to uranium ratio is increasing drastically. Close to this place, the thorium to uranium ratio is about 40. So that means the amount of monazites are increasing drastically, firstly because of the last marine regressions and transgressions and regressions and so on. So this is very, very important that we can use the dose rates, that is radiation dosimetries. We have put about 20 along this area for seasons, various seasons. And last time we have made some measurements. Some of them got lost because of the present COVID situation, but some of them we could retrieve. Now we have put about 20 uh, uh, more dosimeters, which Professor Dhole has been kind enough, Sanjay Dhole, and we are putting it, and we are keeping a close watch. And this is the outdoor dose rate, not the indoor dose rate, outdoor dose rate, because that is very important for our modeling work, which we are doing in terms of this thing. So this is some sort of a swash zone, the berm, the dune, and you see, based on spatial distribution, I can tell you which is the dune, which is the berm, which is there. In future, we want to supplement it with low altitude drone based data. Presently, because of the pandemic, we are not able to fly the drones, but low altitude, 10-meter, uh, these topographically hugging radiometric devices, we are going to fly in drones, and we are going to try and supplement this data, which we have done with ground based data. Okay, so this is very, very important. So integration of ground based data with drone based data and geospatial data, which I will show later on. So please remember that this sort of a spatial listing with great reliability can be done. Otherwise, and these berm and these dunes and the fossil dunes means they have got stabilized, they are not going to move with aeolian activity, that is wind activity, and so on. Now, this is here we have done a 2D resistivity tomography, and here another very important thing we find that most of the radioactivity data and base row, and this is the comparison of the GM measurements and the thorium, and then you see that the resistivity data indicates that very, very low resistivity. How much? 0.1 ohm meter to 1 ohm meter is very, very conductive. You see the blobs, these blobs with low Geiger-Müller data. We have taken these samples, we have measured in the lab, and we know for sure how much thorium and uranium is present. So this is the field-based data using Geiger-Müller detector. These are very low resolving time Geiger-Müller counters, very sensitive. Okay, and partly some of them have been repeated by scintillation spectrometry. So this is the thing which now these are some of the data points which we have taken core 1, core 2, core 3. There are numerous cores we have taken, and we are trying to date it using OSL. But apart from that, the dose rate data is also very important, because over seasons, over year, how much is the dose and what is the variation, that can be a very good uh, data for the OSL ages. Why? Because is the denominator, that is the dose rate data, is varying with time, but say yearly basis. So it also serves as a baseline calibration. Baseline means once we have done it, say 2010, 2011, any enhancement will be reflected based on that, because we are using similar type of methodology, integrated methodology, geophysics, geology, as well as dosimetry. So please remember, without that, I think we are lost. In most of the cases, I see a lot of publications which are completely lost. Now, here the rare earth, you see that we have a small anomaly here. Uranium is depleted. There are reasons for that because of a mineral plagioclase, and you see lanthanum, cerium, samarium very, very high, and then dysprosium, and these things are very, very high. Now, we are also working on another area in Andhra Pradesh where yttrium, another heavy rare earth, is very high. And please remember, the cost of these minerals, apart from being strategic, apart from being critical, is reasonably high. If I'm talking about rare earth oxides, and of course applications, I can tell you few hundred applications, and next generation of computers are all going to depend on rare earths. Okay, so these are some of the things as a depth, how the variation takes place, the abundance of elements, and then of course, now another thing which we have done, and we are presently continuing with this fact is that we have taken the land surface temperature related to the change. Now, this is based on the satellite data and 2014, 15, 16, 18, 17, and then 16, 15, 16, 17, and we are going further. Now, we find some changes. We are trying to quantify these changes. Now, this is a broad spectrum. We are looking at uh, slices of this using what is known as the ASTER data. The satellites which have got special ASTER. They look in the infrared region. Now, why? The reason is that all these minerals, radioactive minerals, that means the region here, the heavy mineral beach places, they are giving rise to certain surface temperature because of the subcrust of the party. But it is also giving some amount of heat because of the pairing thorium or uranium, if present in the form of zircons, to decay to the daughter, and that is known as radiogenic heat. So the amount of geothermal anomalies based on satellite data, typical satellites in particular bands will show that the geothermal anomaly is going to indicate along the coastline, the entire coastline. It can be integrated with our handheld data, if possible, UAV data, drone based data, and the laboratory based data, the radiation dosimetry, and of course, the geospatial technology. So please remember, for large area, you require a reconnaissance measurements. And now, during this pandemic, going to field and collecting samples and doing analysis is absolutely not possible. But you have this data in various satellite, you know, domains. So we can use that satellite domains, and this remote sensing data is can be used. And this is going to be very important for these because these are rich in thorium and uranium, and the radiogenic heat is going to be more than the emissivity or the albedo, which is the primary component of normal land surface temperature. Okay, so we have
Professor,
done some. Yes.
5 minutes, please. You have more 5 minutes on. Okay.
Oh, 5 minutes. Okay. So I think it is wonderful, Susan. Ending up here. So uh, India is known for the thorium present, the beach places compared to thorium to uranium ratio. It is 1 to 30, but now this is a older presentation. We have come to 40, higher than the crustal average. 3.8 is a normal crust on the planet Earth. For Mars and other things, there will be different values. The majority of elements uh, experience are up to depths of 2 to 2.5 meters. Please remember, hafnium and all those things are also very, very important for strategic things. The early action related to cyclones and storm surges and the fluvial actions are responsible for the distribution of heavy minerals on the beach. And please remember, beach not only are of tourist interest, not only of temples and etc. There are other things also, and if we lose land along the beaches, it is going to be catastrophic. Okay, so these are some of the things, and I say thank you, muito obrigado. This is a particular species of animal, means a turtle, which is known as Oliver Ridley turtle. Now, this comes at a particular season, generally March and April, and lays eggs. Few thousand, 100,000 eggs. They come from the sea, shallow sea, and lay eggs here and go away. These are almost endangered species, and there's another endangered species in this land which will be getting affected if we mine various type of rare earths without bothering about how to sustain that. So I'm not going into the mining aspects because we have decided on a methodology and we are publishing some papers on that aspect. These are horseshoe crabs and which are also getting endangered. So this area where these Oliver Ridley turtles and other things are, coming every year, they are slowly decreasing in number and getting more endangered. And so, sustainable mining of rare earths is very, very important. Apart from various to humans also it gets affected. So I don't want to go into details. Thank you again for your kind attention. Muito obrigado.
Thank you,
If there are
Professor
questions, I'll be
Sengupta. A very interesting presentation, and I think it's very important to talk about this kind of view that normally people do not know that many industries that do not use radioactive materials accumulate the norm and radioactive materials for their cycle. For example, oil and paper industry accumulate radioactive material during their process, and these materials cannot be simply returned to the environment. And especially now that we are really needed is renewable energy, but this renewable energy will require massive increase of our existing extraction levels, as you told, the neodymium, that is an essential element also for wind turbines. And I heard that it's expected to increase extraction by almost 35% over the current levels. Indium for solar panels, that is 920% increase in this extraction. Lithium for batteries, 2,700% from these extraction levels that we have now. So can you comment on this? Do you believe this extraction should be more advised for people to know also this bad side of renewable? Because really we need them, but they have a bad side that people are not talking about. Do you believe this increase this increasing extraction will increase too much environment radioactivity in a dangerous level?
Yes. Actually, one of the things is that while mining, most of the countries use dredging. Now, dredging makes the beach to be more eroded, close to the beach, right? So, dredging should be stopped, and there are mobile mining methods which should be used. The other thing is, when you extract UDBM and other things, there are a lot of soil and the groundwater gets contaminated. Please remember that we did some study, we have published it also. Most of the after use, we are buying new and new mobiles, and presently the number of mobile phones have increased drastically, new ones, Apple and various other companies, right? Now, the unused mobiles, only a small fraction is, some material is extracted, the rest is dumped somewhere. Now, please remember, most of these minerals, most of these elements like neodymium and other elements are highly toxic. So if they enter the food chain or they enter the water supply chain, then we are calling for our own extinction. Okay, we are trying to hasten up our extinction. I understand carbon dioxide, sulfur dioxide, etc., etc. But when you extract, right from mining to extraction, for example, where do you throw the mobiles? Do you dump it in some places after extracting some of the elements? Even burning coal, you cannot burn. Coal has a reasonable amount of radioactivity. Some of them have a high radioactivity. Now, burning coal, all the radiations remaining in the fly ash as well as the bottom ash or pond ash. And that radioactive, that material, if it is used, And even the atmosphere is having the effect of radon and thoron, because the entire flash is not trapped in the entire uh, thermal power plant. So some of the plant from the precipitators, they go out. So what we are trying is that this soot which comes out, small particulate matter, 25 microns to say 900 nanometers, these are highly dangerous. These are highly dangerous in the sense that we inhale it, it migrates to long distances. It's no more a local contaminant, it is a global contaminant. And please remember, this is also, for example, use, after hydrofracking of shale gas, in United States of America and most of the countries I know of, they are keeping in a repository. But suppose if there's a leakage in the repository, then the entire groundwater gets contaminated by radium and radon. So, what we are doing, and not only that, this causes induced seismicity also, because some of the areas, since they get a lubricant, that water, they start getting seismotectonically active, and you get quite a lot of places in USA had 4 to 5 micro seismicity on the Richter scale. So please remember, see, when we utilize material, we should look for suitable any energy resource, anything. Remediation is a must, and optimization is another important thing. Most of the industries, whether you talk about hydrocarbons, not only they give rise to a lot of sulfur dioxide, carbon dioxide, they give a lot of radioactivity. The oil slags, they have radioactivity. Okay, so
We have
long
here
pipeline.
because I am in a state where they extract a lot of petroleum from the sea and from the countryside. And some years ago, I had one student doing a PhD about this problem: what to do with that slug, where to put it. We didn't have legislation because it's not a very high level, but also not a level that you can put in the environment. So people are not thinking much about these problems. As you told, solar panels, after 25 years, what to do with that kind of trash? We need to think all the cycle, what we will do, how we will manage these things.
Actually, this
And
designing of suitable repositories for these things, because see, even if it is intermediate level radioactivity, right? When it becomes cumulative, a lot of material is added up on top of it. This becomes problematic. See, if you have a few kilograms of some waste, it may not be problematic. But if you have few thousand grams or a few tons, then of course it becomes more.
yeah.
And most of the industries dump it in some sites which is open, and both spatial migration and vertical percolation goes on. So we are calling for something which is catastrophic, and we don't understand, what is happening, whether low dose is really not leading to any chromosomal aberration. I don't think, because most of the countries believe in LRR as low as reasonably achievable. So the output waste has to have radioactivity as low as reasonably possible. You cannot just decide on a cutoff number, just radon 200 becquerel per meter cube. But suppose most of the countries now are reporting very high radon. Go to States, go to Canada, indoor radon is increasing drastically. Okay. The other thing is, even any synthetic material, bed mattresses in South Korea, they are found to have very high radon. How much? More than 600 to 800 becquerel per meter cube. And this is all published data, open domain data. So any synthetic material, after you reuse it, that is going to create a problem. We have to be very careful. For example, you have cobalt 60 source and the lead around it. You utilize it from something, melt it and utilize it. That is not a solution. I don't think that is a solution. So, X-rays. after its long life, long number of X-rays, that entire X-ray tube, that Cooley's tube, has to be kept in a suitable repository. You cannot just keep it, throw it in some groundwater, ponds, lakes. No? I don't think that is that we are calling a catastrophe. Because see, sulfur dioxide, carbon dioxide, they are models. We can do some atmospheric modeling, and Professor Manabe has shown that it is almost 2.36, which is very close to 2.6 degrees centigrade expected rise. So modeling can be done. But what about radioactivity? See, people should not only bother about radon, people should also bother about thorium.
Yeah.
And there are other radionuclides associated, cesium, for example, and artificial radionuclides, which are contaminating. And this, and the extinction of these Oliver Ridley turtles, horseshoe crabs, and various other uh, animals, and benthic and other foraminiferas. This is telling that mankind is going to follow that same cycle. For example, plants, they hyperaccumulate a lot of uranium and thorium. And if we take it, for example, I don't think you can eat radish or turnip from Ramsar in Iran. If you eat it, okay, fine. Nothing to say much about it. So,
Yeah, normally people are just worried about nuclear power plants, and they are afraid of nuclear power plants, and they don't see these problems in other industries. So I'm always
yes, actually,
defending that the nuclear should be more important in this time where we need more energy, but we need to preserve the environment. And people are going in the wrong direction. I believe we should help they understand a little
yes.
bit of that, the dangers.
Let me tell you. See, earlier, people are not worried about smoking. Then there were a series of things, and epidemiological studies were done. And now, most of the big tobacco companies, including in India, they're making vegetable oils rather than making cigarettes. Okay, so the transformation has occurred with service smoking. Now, I believe that radioactivity, including radon, which is the second largest cause of death in USA due to lung cancer, is also going to create a lot of problems in various, stone crushing industries and various other, mining industries, because we are inhaling this fine particle matter, and that is going to create a problem. Before we know, I think the thing has settled. So one has to be, very, very cautious that what we are doing, is it the right way to do it, or are we calling for the extinction of the human race? I agree, CO2 and sulfur dioxide, etc., are problematic, or methane, but these are equally important. In the next, decade, we will find rare earths in almost all the technical, what we call gadgets and
Yeah,
equipments. Then what do you do? So
yeah,
I'm
very
into,
problem. Professor, I think we should stop here because we are late. We started a little late, so we
okay,
delay a little bit here, but we need to move for the next one. Well,
okay, okay.
I don't see any question from the people here in YouTube, but they made a lot of compliments to your presentation. It was very nice, really. Thank you so much, and
Okay.
let's move for the next presentation.
Okay,
Okay?
thank you. Okay, thank you.
Bye. Thank you.
Okay, bye. Muito obrigado, and nice talking to all.